Hi everyone, in this lesson I'm going to talk about LPO development. Plastic deformation of a polyphase material produces two types of fabrics. One is shape preferred orientations, SPOs. They are due to alignment of grain shapes as finite strength increases. Another type of fabric is called lattice preferred orientations, LPOs, or sometimes crystallographic preferred orientations, CPOs. They are defined by alignment of lattice orientations. In the materials science literature, LPOs are commonly called texture. SPOs are directly observable in outcrops, on hand samples, or in thin sections, depending on their size. On the left here is a quartz malonite. One can see clearly that dynamically crystallized quartz shapes define a beautiful SPO. So the subvertical foliation here is defined by the shapes of dynamically crystallized quartz grains. On the right is an outcrop image of a deformed conglomerate. Again, there is a subvertical foliation defined by the alignment of the elongated pebbles. LPOs, on the other hand, are not directly visible. On the left here is a quartz feldspar malonite from the Granville-Franc tectonic zone. The thin section was cut parallel to the stretching lineation and perpendicular to the foliation. The shape fabric is very clear on this image. However, the lattice preferred orientation in quartz must be measured separately. Traditionally, the quartz C-axis orientation can be measured with a universal stage attached to a petrological microscope, and the measurements are then plotted on an equal area projection, either scattered plot or countered plot for further interpretation. Nowadays, new technologies like EBSD, electron backscatter diffraction, which is a device attached to a scanning electron microscope, computer-integrated polarized microscope, etc., allow us to determine the lattice preferred orientation of rocks more efficiently. Keeling et al. Used the CIP, computer-integrated polarized microscope, to measure in situ quartz CPOs from a malonite thin section. It is quite impressive that one can have such in situ acquisition of CPO data. They found out that quartz CPOs are quite variable, even in a single thin section. Although there are other mechanisms, most LPOs are produced by dislocation creep. Other deformation mechanisms, like diffusion, tend to weaken or destroy an existing LPO. Dislocations take place on slip systems. A slip system consists of a slip plane plus a slip direction. Quartz, for instance, has many slip systems. Basal A slip system, so the basal here is a slip plane. A is the slip direction. Prism A slip system, prism C slip, and a rhombo A slip, a rhombo C slip. So quartz can have many slip systems. The activity of a slip system in a mineral is defined by its relative critical resolved shear stress. The higher the critical resolved shear stress for the slip system, the more difficult to activate the slip system. In computer modeling, people have assigned different relative CISS for different slip systems. For instance, at a relatively low temperature, the basal A slip system is the weakest system. At higher temperatures, easier slip systems are prism A or prism C slip systems. People have assigned different relative CISS to represent the relative activity of different slip systems. The critical resolved shear stress for a slip system depends on many factors. It depends on pressure, temperature, water viscosity, etc. And it is not fully understood how these factors affect CISS of a slip system. each slip system is like a simple shield. It must work with lattice rotation to accommodate strain. As shown here, a crystal here, A, B, C, D, accommodate vertical shortening by a slip on one slip system. As the slip takes place, the crystal direction perpendicular to the slip plane must rotate clockwise. Therefore, the operation of a slip system must be accompanied by lattice rotation in order to accommodate an imposed strain. So the rotation of lattice of all grains in a rock will lead to the development of lattice preferred orientation. The earliest model for LPO development by dislocation mechanisms is the Taylor-Bishop-Hare model. The model assumes that strain is uniform across all grains, and the strain in each grain is achieved by slip only, and the strain compatibility is strictly maintained throughout the deforming material. Here is a two-dimensional explanation of the Taylor-Bishop-Hare model. So the undeformed aggregates of the polycrystal material is schematically shown by E here. In a deformed state, it's shown by F. So every crystal has been deformed by the same amount of strain. So the strain is strictly uniform in all grains. Let us see the strain in one grain by slip. So there are two slip systems in this grain. The motivation is for this grain to achieve the final shape like this and in that orientation by activation of slip system 1, this blue slip system. It can change the crystal into this shape. However, it will never be able to change to this required shape. Another slip system must be activated. S2 must be activated. Although the operation of the two slip systems lead to the final shape, the orientation is not right. So it must have an additional rigid body rotation to rotate the lattice, such that this grain will attain the final shape and the final orientation. Therefore, two most important points here. One is, for two-dimensional deformation to achieve the required strain, a minimum of two slip systems are required. Second, the crystal lattice must rotate in general. So the Taylor-Bishop-Hare model explained in 2D can be extended to 3D easily, except that in 3D, a minimum of 5 independent slip systems are required to accommodate an imposed deformation, and this is called the von Mises condition. There are many ways to demonstrate why a minimum of 5 independent slip systems are required to accommodate an arbitrary strain. One demonstration is presented here. An arbitrary strain can be represented by a strain tensor. Because dislocation creep leads to incompressible deformation, this strain tensor must be incompressible. Therefore, epsilon 33 can be written as negative epsilon 11 minus epsilon 22. Now, this arbitrary strain tensor can be written as a sum of these 5 independent components. In the session on flow and deformation, it will be demonstrated that each of these can be achieved by a simple shear. And each simple shear can be realized by an independent slip system. Therefore, 5 independent slip systems will be able to realize any imposed deformation, any imposed strain. Independent slip systems means the operation of a slip system doesn't interfere the activity of other slip systems. Gordon Lister in the 1970s did a PhD on the development of quartz CPO using the Taylor-Bishop-Hare model. This diagram is from one of his publications. And his work has been the basis for the interpretation of quartz CPOs in natural malonite. The Taylor-Bishop-Hill model is highly unrealistic. The assumption of uniform strength throughout all grains is quite ridiculous. A mechanically sounder model is the self-consistent viscoplastic model, VPSC model, that was developed in the later 1980s and early 1990s. The model is based on Eshelby's theory of an inclusion in the homogeneous medium. Eshelby's theory relates the stress and strain in an inclusion, local field, to the background macroscale field. So a quartz grain is treated as an inclusion. It interacts with the polycrystal continuum. The polycrystal continuum is a heterogeneous medium, of course. It is treated as a homogeneous equivalent medium. The property of the homogeneous equivalent medium is obtained by homogenization, that is due to Eshelby's theory. The interaction of a grain, a quartz, with the polycrystalline material, quartzite, is approximated by the partitioning equations due to Eshelby's theory. So the strain rate in a quartz grain is related to overall macroscale deformation in the quartzite by a strain partitioning tensor. The vorticity, which will lead to the lattice rotation of the quartz grain, is related to the overall strain rate and vorticity also by a partitioning equation due to Eshelby. So solving the partitioning equations and homogenization equations simultaneously leads to this self-consistent model. As deformation goes on, the homogeneous equivalent medium, which represents the quartzite as a whole, will develop anisotropy due to LPO development, and that is considered self-consistently in the model. Partitioned strain rate and vorticity, that is the local field, will determine the lattice rotation of that grain and the strain of that grain. The VPSC model has been widely used fairly successfully in materials science and earth sciences. A most recent application and development is by Bandari and Zhang. We modeled quartz LPO development in different flows from pure shear to simple shear, at low strain to high strain, for various models representing different combinations of critical resolve shear stress to represent different deformation temperature conditions. We were able to produce all field observed quartz CPOs. We also embedded the VPSC in a multi-scale model to achieve multi-scale modeling. This is pretty much the current status of CPO modeling for quartz. There are still issues with LPO modeling. A major one is how pressure, temperature, stress, and water fugacity affect the critical resolve shear stress on slip systems. In current modeling work, like ours, we assign relative critical resolve shear stress for different slip systems to represent different combinations of slip systems for different temperature conditions. This treatment is qualitative, empirical, and somewhat ad hoc. So the transition of CPOs as deformation conditions change needs to be better understood in the future. So this is my brief introduction to LPO development in rocks. Thank you for your attention.